We are looking at Section 7.4. In this lesson, we'll look at solving problems that involve the application of exponential functions. So we've already did something like this before in Chapter 6, yet this time we're going to be able to use logarithms to help us solve exponential functions. So first of all, let's recall going from logarithmic form to exponential form. For example, we have log 27 base 3 is equal to x. Then when we put it in exponential form, it's the base to the power of x is equal to 27. If we're looking at a natural logarithmic function, the base is e, so e to the y equals x will be the exponential function. We're also going to look at the change of base formula. So for evaluating any logarithm, we can use the change of base formula. For example, if we have log 27 to the base 5, if we were asked to evaluate this, this would be equal to log 27 divided by log 5. And of course, each one of these are able to be calculated using the calculator since they are base 10. In the last section, in Section 7.3, we looked at the laws of logarithms, and there's the product law that says the sum of two logarithms with the same base, then we can multiply the argument. When combining logarithms, a difference of logs, we can divide logarithms. This is the quotient law. We can divide the arguments. And the power law says that if n is to the power of m, then we can bring it in front and multiply by the log. So first of all, let's review some exponential application problems. We did these questions before. The population of trout growing in a lake can be modeled by the function p of t equals 200 times 2 to the power of t over 5, where p of t represents the number of trout, and t represents time in years after initial count. How long will it take for there to be 6,400 trout? So when we substitute 6,400 into the formula, we get 6,400 would equal 200 times 2 to the power of t over 5. And we're solving for time here. It says how long, so we're going to solve for t. What we did in Chapter 6, we took the 6,400 divided by the 200 to get the power by itself to equal 2 to the power of t over 5. Then this would give us 32 to equal 2 to the power of t over 5. And then we wrote 32 as 2 to the power of 5 equals to 2 to the t over 5. And then, of course, we made the exponents equal to each other. 5 equals t over 5, so 25 would equal t. We're going to see now that there's another way of determining the value for t in this section. What happens if this number cannot be written as the same base? What happens if two sides of the equation cannot be written as the same base? And we are going to solve problems like this. If you recall another exponential application problem, a deadly bacteria doubles in size every 3 hours. If there are initially 250 spores, how many are present after 7 hours? So we have 250 is our initial amount, and the bacteria doubles, so 2 is our base, and it's time over 3 because it doubles every 3 hours. So if we're looking for our final amount, we are going to substitute 7 in for t. That would give us A would equal 250 2 to the power of 7 over 3. That would give us our final. Of course, the initial and the final should be in the same units, and time will be in the same units. A half-life of a radioactive isotope is 30 hours. That gives us B as a half. That's our half-life formula. How long does it take a sample of 1,792 milligrams to decay to 56? So 56 will be our final, and 1792 would be our initial. It's a half-life problem, and it would be T over 30, since it takes 30 hours to become half. In the last problem, we have a financial application problem. $3,000 was invested at 6% per year, compounded quarterly. What is the future value in 4 years? So we would have A equals our principal, 1 plus the interest, to the power of the number of compounding periods. In this case, our principal is our $3,000. We're solving for the future value after 4 years, so this being time, that will go in with the compounding period. We would calculate the compounding period and put it in for n. So let's look at this example. Yvonne has a balance of $3,215 in her savings account. This account pays 2.4% interest per year, compounded annually. The compound interest formula is this. How long, it's asking us for time, how long will it take for Yvonne's balance to reach 5,000? So we have the final will be 5,000, will equal the principal, which is our $3,215, 1 plus, and I in this case, I is equal to the percent, which is 2.4%, divided by 1 compounding period per year, which gives us 2.4%, or 0.024. So it's 1 plus 0.024 to the power of, it says how long will it take n. We have to determine what n is, the compounding periods. So in doing this, the first thing we have to do is get the power by itself, isolate the power. So we'll have 5,000 over 3,215, which will equal 1.024 to the power of n. This will give us 1.55520 and so on, 1.024 to the power of n. Now we will take the log of both sides of the equation. Since we're trying to solve for n, we're going to take the log of both sides of the equation. We can take the natural or the common log of both sides of an equation to preserve equality. And now, because of our laws of logarithms, the power law tells us n can come down in front and multiply by the log. This will give us log 1.55520 is equal to n times log 0.024. Now we're solving for n, yet it's being multiplied by this log. So we know that log 1.55520 divided by log of 1.024 is equal to n. This will give us 18.53 equals n. So we're talking about 19 years. So let's look at the next example. The intensity of light passing through water can be modeled by the equation I equals 10 to the power of 1 subtract 0.13x, where x represents the depth of the water in meters, and I represents the light intensity in lux. Most aquatic plants require light intensity of 4.2 lux for strong growth. Determine the depth of the water. And remember, the depth of the water is x. So we're going to solve for x in this case. We're going to put 4.2 in for I. That's going to equal 10 to the power of 1 subtract 0.13x. Once again, we're solving for the exponent, so we'll take the log of both sides of the equation, the common log, both sides. And we have now, using our power law, this can come down in front of the log. So give us log of 4.2, which will equal 1 subtract 0.13x times log 10. Now the common log of 10, that would just be 1. But we'll continue with the same procedure. We have log 4.2 divided by log 10 will equal 1 subtract 0.13x. And so we have negative 0.37675. Sorry, we're going to move this 1 on the other side of the equation to isolate the x part first. This will give us log 4.2 divided by log 10 plus 1. Sorry, subtract 1. So equal negative 0.13x. This now will give us negative 0.3765675. That equal negative 3x. And so we see that when we go negative 0.37675 divided by negative 0.13 equals x, we get x to be 2.898 equal x. So that will say that the depth of the water will be 2.898 meters. Let's have a look at the next equation. We have an equation A equals the initial amount times 1/2 t to the power of t over 15. Represents the population of a town that halves every 15 years. It's actually a half-life problem, where A represents the population remaining after time. How many years, here we are looking for time again, will the population decrease by 75%? So if it decreases by 25%, that means that 75% would be left over. So if the initial amount is 100%, and the final amount will be 75%, that's how much it would be if it decreased by 75. That is, if it decreased by 25% rather, if there was 100 first and it decreased by 25%, there would be 75 as the final. So we'll use these numbers. And so we would have, once again, isolating the power, we'd have 75 over 100, so equal 1/2 to the power of t over 15. 0.75 equal 1/2 to the power of t over 15. We'll take the log of both sides, the common log of both sides. This will give us log of 0.75 to equal log of 1/2 to the power of t over 15. We will bring the t over 15 down in front. This will give us log of 0.75 to equal t over 15 multiplied by log of 1/2. And so now we're going to move the log of 1/2 on the other side to help solve for t. It's log of 0.75 divided by log of 1/2 equal t over 15. This will give us 0.41537 so on equals t over 15. So t will equal 0.415037 times 15. T will equal 6.22. So how many years? Over 6 years, about 7 years. Is when the population will be decreased by 25%. After taking cough suppressant, the amount A in milligrams remaining in the body is given by this formula, an exponential application formula, where T is given in hours. What is the initial amount taken? The initial amount will be 10 milligrams. What percent of the drug leaves the body each hour? So, since the B is 0.85, it must be decreased by 15%. How much of the drug is left after 6 hours? So we're trying to find the final amount when we put 6 in for time. So that will be A equals 10.85 to the power of 6. And this will give us 3.77 milligrams. How long is it until only 1 milligram of the drug remains? So we're looking for time. So 1 milligram would equal 10 times 0.85 to the power of t. So we're looking for t. Once again, we're going to isolate the power. 1 over 10 to equal 0.5 to the power of t. So 0.1 equals 0.85 to the power of t. Now we'll take the common log of both sides. Log of 0.1, which equals log of 0.85 to the power of t. And now we're going to move the t down in front, as we always do here. It's log of 0.1, which equals t times log of 0.85. And so since we're solving for t, we would now have log 0.1 divided by log 0.85, which will give us t. And we get 14.16 will equal t. So the drug, only 1 milligram of the drug will remain after 14 hours, 14.16 hours. So we have $1,000 invested at 6% per year, compounded monthly. Once again, how long in months will it take for the investment to triple in value? So if the initial investment, the principal is 1,000, and we want to know when it triples, that means it's going to be 3,000 to equal 1,000. Now for us, I is going to equal to 6% divided by 12, since there's 12 compounding periods for monthly. This will give 0.5%. So it'll be 1 plus 0.005 to the power of, and n is going to equal, we're going to figure out what n equals, the number of months. So we take the 3,000, we divide it by the 1,000 to get the power, 1.005 to the power of n, to isolate that. That gives us 3 equals 1.005 to the power of n. Now we'll take the common log of both sides. And as before, we're going to bring the n in front. So we'd have log 3 equals n log 1.005. So now log 3 divided by log 1.005 equal n, and that will give us 220.27 equals n. How long in months? This will be the number of months. The number of years will be 18.4 years. So we're saying it to be 221 months to triple in value. In summary, we are solving exponential application problems. When we're looking for the exponent, either t or n, we're looking for time, we either have to write both sides of the equation with the same base, or we can take the common log of both sides. And taking the common log of both sides will work for any problem. Remember that there's for your compounding periods, and the interest rate per compounding period. For daily, it will be 365 times per year, and I will equal the annual rate divided by 365. So this is important when we're calculating the compounding periods and when we're calculating I.